scientist in different projects, and there I will have my first talk about this topic, scalable real-time anomaly detection. This is about a prototype developed at Consistor in different labs. And yeah, it's the first time we present this application and the idea behind it. So I hope you can give me some feedback afterwards. And yeah, this it was supported by MongoSoup, this project. MongoSoup is our MongoDB as a service solution, and the project also uses MongoDB in the backend. So I will talk about anomaly detection and explain what is anomaly detection and why we need it. I will explain how we use the AWS infrastructure and MongoDB to have a scalable solution for the anomaly detection application, and how we realize the scalability on different levels. And in the end, I will show a sort of live demo. I will just show the dashboard. And yeah, maybe something more, but we will see. So why do we need anomaly detection, and which kind of data do we monitor with this application? It's most times about time series data and streaming data. For example, in application monitoring, you have something like page views, page load time, CPU load, internal memory usage. This is all data which is constantly generated and monitored. Probably you have New Relic or App Dynamics, some applications which collect these data and show you some nice graphs and generate alerts. The other big area is buzzword today is Internet of Things, where you have a lot of data also coming from different sensors, which constantly collect data like temperature, power consumption in your household, or maybe in some new cars, which a lot of sensors also monitors a lot of streaming data. In this talk, I will show some examples about application monitoring, because I think this is a topic most of you know and use every day. So here's an example from New Relic. And you see these are 7 days, and the page views in these 7 days, and they have a common pattern, as you see immediately. So during nighttime there are few users, and during daytime you can maybe recognize the pattern that is in the morning, during lunchtime, and at the evening peaks compared to the time in between. And I will come back to this graph later, but I want to show you that this is the kind of data we want to analyze this application is built for. So have time series data means that this data follows a certain pattern. Depending on the time data is generated, and maybe the data during the time, or the data you observe in a certain time is dependent on the data or the time data which was generated before. So there's some dependency between the data points. So how do we identify values that lie outside of a normal range? This is a question we ask if we wanted to detect anomalies inside of our data. And the main question is how can we define a normal range, or what is normal in this case? So if we go back to this page views example, you see you can say 10% is normal, because this data constantly varies between day and night time. So you can have a fixed value and say this value is normal. And for example, for response time, if you monitor the response time of your application, you could say, okay, normal response time is between 150 milliseconds and 500 milliseconds. And the response time varies, of course, depending on the load of the number of users on my web page, but yeah, everything between these dotted lines is normal, and everything outside can be considered as an anomaly. This works for response times, but it doesn't work for page views, because it's normal that you have less page views during night than during day. So how can we solve this problem with a more intelligent approach? What we have to do is that we compute a statistical model for our time series and compute values which we expect for a certain time. So we have this example that the data varies between day and night, and at lunchtime we have the highest peak maybe. We have also just discussed it for Amazon or some shopping websites. You have also peaks during Christmas. There are much more users on the website than during summer when there is holiday. So we can try to collect all this data we have seen already and build a statistical model to predict what we expect to see during a certain time. And then we compute the difference between what we see currently and what we expect for the current date. So, and this difference, we take this difference and say, okay, the deviation between what we expect and what we observe can be maybe 10%, but everything above 10% difference is an anomaly. And this is the approach we take for anomaly detection with a statistical model. And to show you how this works, we got the New Relic API. We took the data from New Relic, pushed it into our application, built a statistical model, and computed the difference between our statistical expectations and the observed values. So you see the blue line here is these are the expected values, and the orange graph is the currently observed values we have. And as you can see, when the difference between the expected values and the observed values is quite high, then we have automatically we detect an anomaly and say this at this point we have an anomaly detected because we expected page views to be about 15, but we observed about 8 page views. And so the deviation is above this threshold, which we consider as normal. Is this clear to everyone, or do you have questions?
So, are you just building are you just taking the window of few minutes before and just computing the medium or something like this?
Yeah, this how you build the statistical model is up to you, so it's dependent on the application. In this case, it's like you say, I took the values, the observations from the last 5 minutes or last 15 minutes, and the observation I had exactly one day before. So this was a simple statistical model, but you can of course improve it, and take into account seasonal effects like summer and winter and so on. But in this case, it was sufficient to have just to take into account the observation exactly 1 day ago and from the last hour, and from these observations I computed the expected value and then compared it to the actually observed value. And if you compare it with this graph, and New Relic just offers this possibility that you define a threshold for alerts. So it's not possible in New Relic to have an alert for metrics like page views, for example. So if the page view goes down, you don't get an alert from New Relic. It's very low level features New Relic offers for automatic alerting. So you have very nice dashboards, you have a lot of insights, but you have log into New Relic, look at your application and see what's happening, but you don't get automatic alerts for this kind of data.
Can you manually shape the threshold? So for example, if you're doing a special event or publishing something, and you expect a lot more page views than normal, you don't know what it's going to be, but you know it's going to be a, shall we say, a planned anomalous event. Can you shape for that so you don't get alerts?
No, in New Relic it's not possible. So
Just ignore them because you get alerts.
Yeah, so you get a lot of false positives, and in the end the operation guys ignore your alerts, and nobody is using New Relic again. So we put a lot of effort in New Relic. We have a lot of applications to monitor with New Relic, but nobody is using it. So it's quite annoying. So yeah, but New Relic has an API. You can get all this data and implement your own monitoring and alerting. At least this is possible. So, as I told you, this is really data from you, which was collected by New Relic, and you could access it via the New Relic API. And to come back to the topic today, we have AWS user group here. So, this is the reason I present this approach here is that we built this application on AWS, and because we wanted to have a scalable solution to connect a lot of data sources to the application, and we have different approaches how to scale this application. So for the streaming data, we can use AWS Kinesis, and Kinesis provides a lot of useful tools and client libraries you can use to implement your Java application and send data to Kinesis. So on the left side you see the producers. Every producer can be implemented as a function in your application maybe, or so you have a Java client library. This is a Kinesis client library you can just use and push the data to Kinesis. You can also push the data, of course, directly via HTTP. And so if you have different data sources, you push, you can all push it to the same stream. And then you can scale this stream by defining or by using several shards inside of the stream. And every data source can be assigned to a partition key, and this partition key is then assigned to a certain shard, and so you can scale. But I will explain it later on in more detail. And on the right side of this Kinesis stream, we have consumer applications. It's called Kinesis applications, these consumers. And for every shard, the Kinesis client library creates automatically a new thread which processes the data. And as Kinesis application, we have Anomaly Detection, which does the stuff I explained before. So we compute a statistical model, we compare the predicted value for a certain timestamp for this data source, compute this predicted value, and we compare it to the observed value, and if there's a difference between observation and prediction is too high, we send an alert, maybe via SNS, to all subscribers of this SNS topic. And additionally, we store all this data in MongoDB to compute afterwards the statistical model. So we have to collect the history, and MongoDB is can also be scaled very easily with sharding, and you can define partition keys. Like you can use the same partition keys like you use in Kinesis for sharding and scaling the application. And additionally we have this graph I showed you, which just accesses the data in MongoDB and displays it. So, as just mentioned, Kinesis provides a Java API, which is quite, I would say, low level, and as a wrapper around it and some helpful tools. There's this Kinesis client library. You use probably if you use Kinesis. It's easy to use it and program and connect to Kinesis. It helps you with scaling. It's fault tolerant. It restarts maybe the processors, which and sets checkpoints. So you can define intervals when you set the checkpoint, and if the application fails in the meantime, you can access the data again after which were produced after this checkpoint. But you find a lot of the documentation, of course, on the Amazon websites, which is quite well documented. The most important concept is Kinesis streams, partitions, and charts. So you create one Kinesis stream, maybe on the web console or via Kinesis client library, and each stream can contain multiple charts. And one chart provides a certain capacity and performance. And then you can, if you have more data sources and add more data sources, you will probably add more charts. And the data is distributed to these charts by the partition key you set on your data. So if you have application monitoring, you probably have a partition key called page views, one called CPU load, and one partition key called response time. And if you have only one chart, of course, all this data is written to this chart. If you have two charts, it's split up. And if you have two charts, the performance increases, and the costs on AWS are computed per chart. Are there some questions? And I want to introduce now these different levels of scalability we use for anomaly detection, which you can use, of course, for different many other applications. So in Kinesis, you have the sharding concept, and for every shard, you have in this Kinesis stream in the middle. This is an example from Spark, which has also a connected Kinesis. So you have here 3 shards, and the Kinesis client library connects to Kinesis, to your Kinesis stream, and automatically creates one thread per shard. So if you have 3 shards, you have 3 threads which process the records you write into the stream. So on the left side, you see also 3 producers, but you could have also more producers, of course. And this data is then distributed among these shards by the partition key. The other scaling takes place on MongoDB. So on MongoDB you can also define shards, and you can use again this partition key already used in Kinesis on MongoDB. So you write the partition key to every document and say, put an index on this partition key and say, this is my shard key, and please distribute my data according to this partition key to the different shards. And every shard in MongoDB is a separate database instance, or possibly also running on a different machine. So it's very easy scalable by defining more shards. What we also do, and we have had some experience with time series data, we defined a special data scheme for this kind of data, for time series data, which means we have something like a bucket model. We have an array data of data in every document. So we put 10 data points in one document, and after we collected again 10 data points, we create a new document. This also improves read and write performance. And then another level where we introduced scalability was the algorithm application level itself. So we used an algorithm called T-Typist, which was developed by Ted Dunning, which is scalable in the sense that it's a kind of MapReduce algorithm to compute the quantiles, so this normal range you need to tell if an observation is outside of this normal range or inside. But I won't go into detail. What you saw maybe on this first slide, that Spark has a Kinesis connector, and Spark streaming is also, Spark itself is a very scalable and performant application and tool. So the plan is, the next step is to introduce Spark to this application to be faster in processing of the data. So I promised a live demo. It's not much to show. It's just this graph I showed you before. It's built with D3 Rickshaw. This is Rickshaw is a framework built upon D3, and it's very useful to display time series data. You can have multiple time series in one graph. So in this case, we have a time series for the observed value, a time series for the expected values, and a time series for the anomalies we detected in the application. And you see the timestamp here. I just move the mouse and the values. It's quite nice. And I also have here this project. I think you don't see so much, but I could run it, but I think it's not much inside here. But if you are interested, I can show you some of the code to explain more details about the Kinesis client library and how we used it.
One question about what kind of data do you ship inside of the Kinesis stream? Do you ship, let's say if we're talking about the page views, for example, do you ship one data point per page view in there, or do you kind of aggregate the data before you ship it? Like, okay, how many page views I have in 1 second, and each second I ship the total sum of page views. Do you, because of the granularity, you understand?
Yeah. So in this case, it depended on the granularity of New Relic. So you can ask New Relic about the data of the last 12 hours or the last 1 hour, and then you get data back in the different granularity. So if you ask for 1 hour, you get data maybe for every second. If you ask for 12 hours, you get aggregated data for every 10 minutes. 15
So
minutes.
right now you have kind of a daemon or something like that, which pulls the data out of the New Relic API, pushes it into the Kinesis in the granularity you get out of the API, and then you do your calculations based on a New Relic API. So you don't have anything like own aggregations or summing up. You don't have the hassle with that.
So I immediately push the data like I get it from the sensor or from New Relic. I push it into Kinesis, and the data is it's a JSON format. Just standard with a timestamp, partition key, and the data value.
Could you maybe say just a few words about the scalability of the D-digest algorithm? I'd just like to understand why does it scale? How do you make it scale?
It scales because you collect, first you collect, so you compute for every observation you have the difference to the expected value. And these differences are just collected and not yet aggregated. So you have a large array or list, something of these differences, and then you can collect all these differences, deviations in multiple threads, and in one step, the last step, you can just say, okay, I compute now my quantile, my 90% quantile, which is my normal range, and everything outside of this 90% quantile is. So you just compute a quantile out of this values I collected.
Okay, but it means the predictions have to be pre-calculated, and the way you pre-calculate them must not always be scalable.
No, the
depends on how your prediction model works.
The prediction is very easy. It's just a regression model, so
it also
we don't need to scale it.
Okay.
It's very fast. The only thing we can improve maybe is to compute the statistical model, to have this computation of the statistical model more scalable, but you don't recompute this model every second. You compute it maybe one time a day.
Okay.
If you're collecting sensor data via Wi-Fi and there's a hiccup, and say the time that comes in, you have two data points with the same timestamp. Is it possible to create a report that shows those instances? Because for example, I know in Cassandra, when that sort of hiccup occurs, it will automatically look for the data that has the greatest amount of text, for example. But that might not be correct in all instances. So if you have two data points that come in with the same time information, is there a report that you can configure that will quickly highlight those instances?
So it's not built into Kinesis or something, but
right.
Yeah, you can you would have to implement it. So Kinesis doesn't take care if there are about the timestamp. The timestamp is just part of the data you push into the Kinesis.
So if you have corrupt data, there's no way to see that and understand where those anomalies lie. Easily, you'd have
okay. Of course, you can implement it.
Not easily.
But it's not part of this application.
Okay.
But we can talk later maybe if you have more questions. Okay.
I'm not sure if I fully understand the need to use Kinesis and all the MongoDB, because if I understood your problem, you are just taking all the number of requests per second from each page, computing the mean from it, and comparing it using sliding window to compute the mean for last 30 minutes or 15 minutes or something like this, and then comparing the current value to do this. So in my opinion, the Kinesis is a little bit too big weapon to do this, because you can do this easily with some easier programming, unless the biggest problem with this approach, I see that you have many workers which are providing you with this data. On the other hand, if you would want to have the anomaly detection, there can be different anomalies. For example, you increase your medium time load, but you do not increase your CPU load. So, for example, something is blocking your web pages. So I could see that the Kinesis would be useful if you would be using some multi-dimensional data analysis, when you have many streams of data, like page, number of requests, CPU load, time, I/O load, time it takes to render one page, number of clients, number of unique sessions, and so on. But this would vastly complicate the Kinesis. This would require many streams, many shards, and stuff like this.
Yeah, so you are right. You are just thinking about this right side, this anomaly detection. And for the anomaly detection itself, we don't use Kinesis. But we have only one application, only one code for all types of time series data. And Kinesis is just used to collect all these different data types and push it to the same application. And this application can use, it doesn't depend on the data type you monitor. You can detect anomalies independent of the data type. But you have the same application, independent of the data type. And Kinesis just collects this data, and it helps you to scale your application according to the amount of data and according to the different data types. So what you mean that for the anomaly detection itself, you don't need Kinesis, but to have one application which scales according to the amount of data, you have to use Kinesis, because a message queue is thought that if you have too much data, maybe during daytime, it buffers the data if the application can't process this data immediately, and it buffers the data for 24 hours. Kinesis buffers the data for 24 hours, so during nighttime, at least, it should be able then to process all your data. And then, of course, you don't have real-time data or real-time monitoring, but if it's in the worst case, but yeah, the sense of Kinesis is to have a stream and a message queue.
I think the idea behind this, if I understand you correctly, is the decoupling between the producers of the data. You can attach as many as producers as you want, and you don't need to care about this in the application itself, because that's all done by AWS Kinesis, right? So it's all about the decoupling between the producers and consumers.
Exactly. Yeah.
So why don't you use SQS or SNS for that?
It's much more expensive.
Yeah, here are the experts maybe. Yeah, if you want to take
No, feel free. But
no, I have not so much experience about the cost.
it's much more expensive, so it's easy as that. If you SQS is paid per message, and if we talk about let's say 1 million data points a minute or something like that, you pay a huge amount of money for only having very, very small packages. And the Kinesis is all about throughput bandwidth.
Yeah.
So you always have the writes and reads per second, of course, but it's much cheaper if we talk about streaming data and if you do the SQS stuff. SQS does a little bit more than Kinesis does because SQS has also the functionality of in-flight and about the dead queues and stuff like that, which is not in Kinesis because Kinesis is only for the streams. And if you're curious about money and have a lot of data, which is a stream or a time series, then you should think about Kinesis and not about SQS because it's just much more expensive.
Yeah, thanks. So I listed the costs here, so it's 3 cents per 1 million put request data points.
What monitors the monitors? So if you're saying, it's getting overwhelmed with data, you're going to get alerts, but a long time later. Is there any way of finding out that you're actually getting overwhelmed with data?
Yes, Kinesis offers some metrics for the streams, latency metric, throughput metric. You can define CloudWatch alerts.
And if it's stopped, if something's stopped, I have this problem at work where things stop and you don't get any alerts because it's stopped. Is there any
What is stopped? Your
well,
monitoring?
the alert systems and stuff, they just stop. Is there any way of, I suppose if it totally stops, it's stopped, but is there any keep alive package around this? It's a bit difficult to do because you need an extra system to see if things are going through.
So if the whole application stops, of course, you have to monitor the monitoring application.
Yeah.
So, to auto-scale, maybe start a new instance of your monitoring again.
Actually, what you can do is that you, I'm not sure if you can do that, but I think you have checkpoints inside of Kinesis. Just calculate the amount of data between after the last checkpoint. If that amount of data increases over a threshold, nobody is consuming out of the Kinesis tree, or it is too slow consuming. And then you need to scale up or restart the application. So always like the kind of heartbeat things you need to do. So that would be possible, I think.
It would be very sophisticated to monitor the monitoring.
Yeah,
but possibly in some applications you have to do it, of course.
You should do it. In some situations you really should do it.
Yeah.
You can get badly burned or something else. You think everything's working, you're notified on exceptions, on anomalies, and you don't get any notifications. That's great. But it's not great because nothing's working and you're not getting any notifications.
Yeah, right. Yeah. But hopefully the standard metrics from AWS tells you already if something is going down.
I need to be woken up. I need to actually be paged or something. So I need a separate system to monitor the monitor.
Yeah, of course. Yeah.
Yeah.
Okay. So if there are no more questions, I would finish my talk, and we can also speak later on, of course, and pass to the next speaker, Antoine.
Should we do a short break?